in this lecture, we will get acquainted with the history and basic concepts of machine learning. So this field of research is based on two concepts. And the first one is inductivity of machine learning. It means that if you have a lot of data that represents a huge amount of special cases, you will be able, after dealing with this data, to form a generalization. Generalization that will be also valid for another data. And the second one means that this resulting generalization allows us to form empirical regularities in the data. To sum up, we are trying to find some patterns by working with samples of pictures, tables, time series, etc. There are three kinds of machine learning. The first one is learning with a teacher, supervised learning. The second one, learning without teacher. And the last one, learning with reinforcement learning. Let's look into them. The first one is supervised learning. This type of machine learning is the most popular among them. Data samples consist of the set of objects that will be analyzed through the learning and the set of answers, correct answers, guided by the assumption that there is such a function that is able to map our set of objects into our set of answers. We are trying to approximate this function through the learning. So, in this example, this function is A. Well, supervised learning allows us to find a solution to a pool of machine learning tasks. For example, classification and regression. They differ in the set of answers. The classification problem contains a discrete set of answers, while the regression problem contains continuous set of answers. For example, if you want to find a lion in a picture, there are only two possible answers. The lion is either present or absent, 0 and 1 respectively. And what about regression? If the task is to estimate the cost of oil for tomorrow, your answers belong to a continuous range of numbers. Let's look at unsupervised learning. Instead of having a set of answers, set of objects together, there is no set of answers at all. The experimenter doesn't know the answers. We want a model to get these answers itself. And this kind of learning helps us in problems such as clustering, where we try to find some patterns for dividing our data into some groups. And for example, in tasks of dimension reduction, where we want to reduce the dimension of our data for simplifying it. And the last one, reinforcement learning. This type of learning can be interpreted as the unusual kind of learning with the teacher. And the teacher's role is played by the environment. You have an agent, your learning system, and this agent lives in an environment. So he wants to be rewarded by interacting with this environment. There is no set of answers, and it is really hard to form that at all. This type of learning is used in tasks of searching of right behavior strategy, for example, if you want to make robots walk. So let's go back to the history of machine learning. The story began in 1943. In 1943, neuroscientist Warren McCulloch and mathematician Walter Pitts published an article on neuron walk. They described the behavior of biological neuron and revealed the main characteristics of this entity in their model. Let's look at the biological neuron. There are a lot of inputs. They are called dendrites, and only one output, an axon. Despite of the fact that there is only one axon, it can transmit signals to several neurons at once. What's more, for a signal to pass through neuron, it is necessary that the sum of impulses coming from dendrites be bigger than a certain threshold. This threshold is an activation function. To sum up, a lot of inputs, only one output, and an activation function that determines whether the signal will pass or not. In addition, neural structures are changeable. Over the time, some of these neurons' connections become stronger, while others break down. It depends on the frequency of using these connections. Here we can see an artificial neuron, a model of biological neuron that was introduced by Warren McCulloch and Walter Pitts. Here you can see a lot of inputs from x1 to xn. Then they are multiplied by weights. Weights characterize the strength of each connection. Then we want to get a sum and apply an activation function to this sum. And in the end, we want to receive the resulting signal y. In 1957, Frank Rosenblatt suggested his model of an artificial neural network, which called perceptron. It successfully solved the simplest tasks. However, solving complex tasks on this model was impossible. It was necessary to multiply the number of neurons and increase computing power. In those years, technologies didn't allow it at all. What's more, there was no algorithm capable of selecting right weights for each neuron's connection. This also slowed down the development of machine learning. Regarding these problems, a book written by Marvin Minsky and Seymour Papert has been published. This book described a pool of problems that arise during the work with perceptrons. Nevertheless, time passed and a method appeared that made it possible to adjust the weights for each neuron's connection. This approach gave an opportunity to minimize mistakes in perceptron's answer. It was firstly described in 1975 by Galushkin and Paul Verbos at the same time. So, algorithm was based on the gradient descent method. However, after this foundation, the interest in machine learning declined again. Despite of the appearance of Year's minimization tool, there was still no enough computing powers and volume of data for high-quality learning process. But time passed, Moore's law was working, and every couple of years, the number of transistors that could fit on one integrated circuit doubled. For example, in 1976, the integrated circuit contained about 8,000 transistors. However, in 2001, this number was increased to 50 million transistors on one integrated circuit. What's more, in the 90s, a volume of data began to increase rapidly, and this allowed to make huge samples of data for learning process. GPUs were created to perform calculations that are related to the graphical output, including interface, games, and so on. Unlike the CPU, the GPU cores contain fewer types of instructions. Their tasks are simple and do not require complex calculations. Losing in versatility, GPUs contain many more cores than the CPU. What's more, GPU's architecture is aimed at performing parallel computing. This architecture is suitable for the needs of machine learning, ideally suitable. More than that, neuroprocessors were implemented. This entity was created for the needs of machine learning. It contains specialized processors for matrix calculations. It gives an opportunity to refuse to access RAM, where the weights are usually stored. In neuroprocessors, we are working at the hardware level. That's why there is no need to load and unload weights from RAM. Research shows acceleration up to 5 times over the GPU. To sum up, thanks to all these methods, machine learning is alive and shows us good results. Thank you for your attention.